Hello and welcome to Lecture 6 on Special Relativity. Today, we will see some remarkable predictions of special relativity on the properties of a light beam as seen by two different inertial observers. These effects are aberration, that is, an apparent difference in the direction of motion of the light beam as seen by a moving observer, and the Doppler effect, that is, a difference in the frequency of a light beam as seen by one observer who is moving with respect to another. These two effects are also expected in Galilean relativity, but however we will see that there is a difference between the effect that we expect in Galilean relativity versus the effect that we expect in special relativity. Moreover, there is a striking, remarkable prediction of special relativity, which is the so-called transverse Doppler shift, which is when you have a source which is moving perpendicular to the direction of relative motion between the source and a detector, you would still see a Doppler shift in the frequency of light. This is something that's completely unexpected from the point of view of Galilean relativity. So let's begin by first discussing the effect of aberration. Now let's consider what happens to a plane wave of light which is propagating in some frame, as seen in some frame S prime, where these are the axes x prime and y prime. And let's assume that this light wave is propagating at an angle theta prime with respect to the x-axis, as seen in this frame S prime. Now, when we think of light as a wave, it has wavefronts. So these wavefronts represent the distance between the peak amplitudes of the light wave. So if we write down the light wave as some kind of wave, which is of the form a times the sine of omega t minus k dot x. Omega tells us the frequency of the wave. The vector k is, or the magnitude of the vector k is what we call the wave number. And this is related to the wavelength of the wave, as k is 2 pi over the wavelength. And the way to think of this wave that is propagating here is to think of it as propagating along the direction k hat. K hat gives you the direction of propagation. And now this quantity in here, omega t minus kx, this is the phase of the plane wave. Okay, so when this phase is an even multiple of 2 pi, okay, so if phase is 2 pi times n, you have a peak in the wave. So what this looks like, if I just plot a snapshot in time, so I fix a time instant and then I just plot what this wave looks like or what the amplitude of this wave looks like, okay, along this direction, what I would see is there's a peak and then there's a trough and then there's another peak. And the separation between these peaks is 2 pi over, is lambda. Okay, that's a physical distance between two peaks. Okay, as measured in the frame S prime. And so if you continue to draw the wave, you can think about wavefronts. Okay, so these wavefronts describe the locations of the peak. So for clarity, let me just draw the wave in yellow. And let me sketch the wavefronts in green. Okay, so this represents a series of wavefronts, and let's imagine that the wave is propagating in this direction. So if it's propagating in this direction, you can easily see that k hat is just this, the unit vector in this direction. So that unit vector can be easily written down in terms of its x and y components. So the unit vector is cosine theta prime in the x hat direction plus sine theta prime in the y hat direction. And therefore the phase of this wave can now be written as omega t minus cosine theta prime x prime plus sine theta prime y prime, where x prime and y prime are the coordinates of the point for which you're trying to talk about the position of the wave at which you're trying to figure out its phase. And now this is only, this part here is k hat dot x vector. So I need to multiply this by the magnitude of k if I want to get this term. And the magnitude of k, as we've seen, is 2 pi over lambda. So I'll just write this out, 2 pi lambda. And the angular frequency, omega, is related to the frequency nu. Okay, so this is the frequency. This is more precisely, omega is more precisely the angular frequency. And so we can write the entire phase in this way. We can write 2 pi times nu times t, where nu is the frequency. And we can pull out the factor of 2 pi as common. Okay, so this is what we have for the phase of the plane wave. Now, if the wave is propagating, okay, so the wave is propagating with a speed c, nu describes the frequency of oscillation of the phase of the wave at a particular location. Okay, so nu describes the frequency of oscillation at a fixed x or a fixed position. And therefore, you already know how to think about this as a plane wave. So nu is related to 1 over the time period for, let's say, the plane wave at this wavefront to make a full oscillation, to go from a peak to a trough and come back to a peak. Okay, so t is the time period of oscillation. And so the speed of the wave would be the time it takes for the wavefront over here to appear to have moved to this position over here. The distance that it covers in one time period would be lambda. Lambda is the distance covered by the wavefront in one time period. And therefore, lambda over t would be the phase speed of the wave. Okay, this is the speed at which this peak appears to propagate in the forward direction. Okay, so the speed of the wave would tell us the rate at which this wavefront appears to propagate forwards. And this speed should be c, okay, for a light wave. For a light wave, this speed is c. Now, one important point is that we know in special relativity now, if we go to a different observer describing the same light wave, so let's write down a second observer.